So my name is Roseanne Sati. I was Tom Sati's wife. We were married for 53 years. So just to introduce myself, and I'm going to introduce our plenary speaker, William WEDLEY. Bill WEDLEY has had a very long relationship with AHP, but let me give you his official credentials first to start. At the Beatty School of Business, Simon Fraser University in Vancouver, Canada, where he specialized in operations management and decision-making. He has had a long relationship with AHP. Let me give you a slightly personal detail here. The first ISAHP meeting was in Tianjin, China, and Tom and I flew from Pittsburgh to Canada and met Bill and his wife, and we flew on a Canadian airline to China. China wasn't very open then, so I think our plane had intended to go all the way to Beijing, but we had to stop in Japan. Anyway, Bill WEDLEY is a very old friend. Our relationship is long, and he is here today so kindly agreed to give us sort of a presentation about his experiences with AHP. He's just a terrific person. So welcome, Bill, and please go ahead.
Thank you, Roseanne. It's very nice. I just like to share my screen here. For my presentation. And I believe you should be able to see it there now.
Yes.
I'd like to thank you very much for allowing me to present. I've been to most of the AHP conferences. There's only 3 I have missed. This is the 16th one. I have a lot of things to say, and I don't know if I'll have enough time to cover them all, so I don't think I'll be able to handle questions during the session. But I would like to draw your attention to my email down at the bottom of this first page here. Anybody can get in touch with me afterwards. Here's a list of all the conferences. As I said, I've been to most of them. This is the first one on the World Wide Web, and I'm looking forward to this experience. This is a few things about myself. I was born in Vancouver, and I went to UBC, got a BCom, went to Columbia University in New York, got my MBA and PhD there. And then I went on to Libya for 3 years in Benghazi, believe it or not. This is before Gaddafi era. And I taught there for 3 years before going back to Simon Fraser and staying there. I've always been interested in qualitative factors, how they affect quantitative decisions. And when I was in 1980, when I was in Australia on sabbatical leave, a friend gave me an article which led me to, in an indirect way, to AHP. It referenced Tom's very first major paper in 1977 about the AHP technique. And it wasn't called that then at that time. But anyway, it had an eigenvector routine in there in BASIC, and I programmed it, put it in, and started to use it. And boy, I found it to be uncanny in its ability to capture preferences. So I was hooked on AHP. First time I met Tom and Roseanne was about 1983 when they visited Simon Fraser University. And I remember at that time they were actually putting the name AHP onto the process. I look at AHPs a little bit like magic or as a black box, because the black box part is what I don't understand. But it is a little bit like magic because it's easy to use, it's intuitive, and it captures preferences. It performs really well. Orrin Cooper has used that term magic, and when I talked to him, I told him I was a little uneasy with it because magic kind of implies a sleight of hand. We wouldn't want that. But when I thought about it more, I thought that, there is a positive magical component to AHP, and it's just the models are complex. And They look like a black box. So I like to look underneath that black box and try to understand what's going on. Now, I want to talk to you today about the idea of functional inconsistency. This may sound like an oxymoron statement, but I've been a very ardent supporter of AHP, but I've been challenged by some of the issues in it over the years. And those challenges are inconsistencies in my mind. And Tom Soddy, he frequently talked about inconsistency as being functional. You want a certain amount of it to provide the impetus to make some investigation and innovate and make advancements. And my career has been about doing some of that, and this functional inconsistencies have been in the background. I'd like to tell you about some of the people who created those functional inconsistencies for me, and I will also present some questions that arose from those inconsistencies. And here are the questions that are behind 9 themes that I'm going to cover. Do we need to know natural zero to do comparisons? Do we need to do all the comparisons? Here's the very important one. Do AHP priorities have a unit? How do you get the full benefit of ratio intensities? Are criteria weights dependent upon alternatives, or can criteria weights be independent of the alternatives? Can derived scales be used as subsequent scales for measurements? And do benefits and costs and priorities have to be commensurate? And can we use this in the supermatrix? Now, central to all these themes is kind of this statement. There is both an advantage and dilemma to AHP. When we derive the priorities, we do not need explicit knowledge of the underlying unit to derive the scale, yet the derived scale has a unit. So that has some advantages. We can get scales and measurements without having prior standards. Although the comparison has a unit, we do not know that ultimate unit when we start making the comparisons. The dilemma, however, comes from that the sum to unity priorities that we usually use have an obscure unit. And I want to explore the obscurity and what that unit is in this paper. I believe that we in the AHP community have not paid enough attention to the units of the scales. Now, different themes highlight different advantages and dilemmas. I will cover those. And here's the first one about natural zero. When I saw this screen for this blue screen and the wall and the buildings behind it, it reminded me of a session in 1998 where Jonathan Barzilai and myself were put side by side on a presentation to talk about AHP and whether it was possible. Jonathan is a very competent mathematician, a very knowledgeable person. And I didn't perform as well as I would have liked to at the time, and that created one of these inconsistencies for me. But Jonathan presented a picture similar to this one here, and he asked the participants to compare the buildings according to height. Now, obviously, you can't do that with this wall there. So then what he did is he removed the wall and he showed the buildings. And of course, now you get a very different picture. There's one building that wasn't even shown. But he claimed that you had to know where absolute zero was, where the origin for the ratio intensities were. And I've kind of indicated them there on that screen. But you know, zero is not important here for making comparisons. Zero is just the starting point for measuring an intensity. And a ratio is really the intensity of something divided by another intensity, which is another something. You can't divide a something by zero. It's impossible. You try it out. Division by zero is undefined. And so I came to the conclusion that, you know, Jonathan is right. You must be able to sense the comparisons, but you don't need to know exactly where zero is. And there's another one. I want to explore a little bit about this. You also need reasonable knowledge. And this is what this slide is about. Michel Bernasconi in Italy did a study, which was very interesting. And he was a good academic. He shared his information with me, and I've analyzed this. But he took 3 problems, and he asked people to estimate the distances from the land, gains of chance probabilities, and the rainfall in these particular towns in September. Now, when you analyze these, and he found this out too, these 2 had good accuracy, and in this one, the accuracy was atrocious. People just didn't know what the rainfall in these various places were. So the moral of the story is you better have some knowledge and expertise of what you're estimating in order to do it accurately. But the other thing that came out is that in all 3 of these, the consistency was good. So the moral of the story here is possibly consistent while at the same time being inaccurate. And so my conclusions kind of are making comparisons is that we're looking for a ratio scale. It's there, but we have to estimate it. And we use a pairwise ratio matrix. Notice I don't call it a comparison matrix, I call it a ratio matrix. I'll tell you about that in a minute. And the values in the matrix are ratio values, and that includes the values that come from the fundamental scale. We're comparing something, the intensity, to another thing. It's never divided by 0. Now, it is a ratio feature that distinguishes AHP matrices from other types of comparison matrices. You can have a comparison matrix, it's not ratio. So I would encourage people to start calling the AHP matrix the pairwise ratio matrix. And also remember, low consistency is desirable, but not crucial, because it doesn't necessarily lead you to accuracy. That's what we should be looking for. Second theme, do we need to do all the comparisons? Users complain about all the comparisons, and only n-1 are necessary to determine the priority vector. All the rest are extraneous. They're extra ones. They help you measure consistency, but I have found in doing work in this area that you get diminishing benefits from the extra comparisons as you get closer to the end of them. So why do all of them? So that's been one of my areas of research on incomplete matrices, how to select the n-1 comparisons, and even a paper on how to predict the consistency ratio if you have inconsistency areas. This is an area where many researchers have contributed to the problem, and they got some good ideas. But what I want to emphasize is you've got to get the ideas into practice, and not many of our computer programs have facility to handle the fewer comparisons. My third theme is my most important one, I think, is do AHP priorities have a unit? I want to use this example here that comes from Tom Sodig and Jennifer Shang about linking across the sizes of fruits across several magnitudes. Initially, I'm going to look at just this top one, these 3 up here. I'll introduce these other ones later on. Let's consider one object. Take the unripe cherry tomato. It has an intensity, and I'm symbolizing it by this interval here, this line. It starts from 0, and this is a true absolute 0. It represents a true nothing, no intensity. Let me introduce a second one, the small green tomato. Now we have 2 objects, A and B. You can see that the small green tomato is 4 times the cherry, okay? With just this one comparison, we can now make scales. For example, here's one where A is the unit, 1 and 4, and B is the unit, 1 and 0.25. The same information makes 2 scales, or a third scale that sums to 1, which is 20 and 80. The ratio is still 4 to 1 in the scale. But in this scale, this is called the relative ratio scale, and this is what we call our priorities. I would claim this has a unit, but it's obscure. Let's have a look and see what it does. Well, I've got a slide in here that gives a definition of ratio scales. I don't want to spend a lot of time on it, You can go up and look at Michelle, who is generally cited for this, but it has an origin of absolute zero. These are properties. You can multiply a ratio scale by any constant so long as it's not 1, and that will transform the scales to new values with a different unit of measure. That's a similarity transform. And if you do that kind of a transformation, you do not change the ratios between the objects. They stay always the same. It's just the measurements that change. Now, here is, I believe I'm on the right, yes, we're on the right slide. Here are my two objects. Here they are as ideal priorities. Here they are as relative priorities. Just different numbers measuring the same ratio between the two. Here in the ideal, the unit is obvious. It is the small green tomato. What's the unit over here? I claim it's an abstract unit of an abstract object. And that object is like being in the cloud. It's a combination. It's some object, which is undefined really, but it has the sum of the intensities of these two objects. So ideal is clear, but it's not clear as to what this object is in relative priorities, but we can think of it this way. Now let me put a third object in. Here is the third one, the line, and you can see if I do the sum to 1, the sum is a different number, you know, it sums up. These numbers have changed, and now it's still 4 to 1 for the tomato to the unripened cherry, but the numbers are different. So these are the ones for 3. Now, if I put them all together, here's the ideal priorities with 2, ideal priorities that are relative with 2, ideal priorities with 3 items, and relative priorities with 3 items. We have here 4 different ratio scales. All of them have a unit of 1. And the thing I want to bring to your attention is this quotation by Sajjad Zahir, who originally said, although these sums all equal to 1, they're all 1 across here, what is often ignored is that a 1 here is not necessarily equal to a 1 there. And I think that is a very good statement to remind us. They all have 1, but they're not the same. You can multiply any of these scales by a positive constant. They'll convert it to a different unit again. And we do that all the time in AHP and ANP, and we don't really keep track of what is happening when that's done. So what I'm saying, or one of the things I will be giving you as a theme in here, is follow the units. You know, when you're looking in commercial crime, there's usually a saying goes, follow the money. Well, in AN and AHP, maybe we should follow the units to get a better understanding of what happens when we aggregate things, because that's when it gets complicated. I'm claiming we should not ignore the unit nor take it for granted. And to understand what's going on, it's useful to do 2 things. Recognize that a 1 here is not necessarily equal to a 1 there. And follow what happens to the units to understand what's going on. My 4th theme is to use the full intensity of ratios. That's the power of our technique. It is a ratio. It's much stronger than an ordinal measure or a rank measure. We should use the ratios to their full intensity. Now here are those 3 again. These are just different ratio scales of the same thing. But I want to demonstrate to you what happens very frequently when we go to a lower order of measure. Here's what happens in many times in multiple attribute utility theory or other ordinal techniques. And I've seen this done. People take the priorities of the AHP and they try to convert it to an interval. Well, what they frequently do is they give the best object a 1, which the line has here, and the worst one a 0, and then establish the value in between for the small green tomato. So now the measurements is on the interval from 0 to 1. But look what has happened. The unit is only a partial amount of this intensity, And number two, the right cherry is given a value of 0 when we know it actually has an intensity. You're losing information here. The ratio scale has a true 0. That's this one. An interval scale has a false 0. I call it false, okay? They call it arbitrary 0. We have a true natural 0, and that's what distinguishes our technique from others. Now, we could even go to ranks, but whenever we go to a lower level of measurement, we're losing information when we do that. So my urging is to use the ratio scales to their real power. So this just repeats basically what I said earlier, that if we ignore the ratio property, lose information and analytical power as a consequence. Now, there's many applications where we can improve with ratio measurements. I'd like to just mention the following. People are doing. Luis Vargas, for example, is looking at voting with intensities. Don't ask which thing or you want to vote for, a person. Ask also how many times. Get the intensity. Enrique Mu, he's doing eyewitness identification. Same idea. Don't just ask, who is likely the criminal, but rather, could this person be the criminal compared to another? By how many times? Use that intensity. And what if we use this in polling? We've recently seen in politics that a lot of polling has not been very accurate. What if they asked when they did their polling, which candidate do you like? And by how many times? Wouldn't that give you a lot more information? So, and you can do the same thing for corporate strategies. Oftentimes, corporate strategies have consensus amongst people. They've said, we prefer this one, but they subsequently fail. Sometimes they fail because nobody ever asked, when they asked about your conviction, what is your conviction to this? How strong is the intensity for this strategy versus that? And that goes through military, government, and other places as well. So my message here is, use the ratio intensities. That's what we have, and we should use our things that way. Now, theme 5 is this thing on our criteria weights dependent upon alternatives. My colleagues, Bert Schoner and Eng Chu at Simon Fraser, we've investigated age techniques, and Bert and Eng have raised functional inconsistency in my mind, which led to our research. A main thrust of it, not only, but was started with a rank reverse problem that was illuminated by Belton and Gear. And our approach was to question how the criteria weights are devised and whether global weights are commensurate before they're summed to get your composite results. Now, Ernest Foreman, the developer of expert choice, used to say to me, you get a very different perspective of how you should fill in the hierarchy if you start from the bottom to the top instead of from the top to the bottom. And what our approach has largely been, my colleagues and I, is a bottom-up one. And when you start working from the bottom up, you're confronted with the question, when you've got the working from the bottom, you have the weights for the alternatives. Okay, what are the criteria weights that will create commensurate values across the various criteria when you add them up in a hierarchy? Now, here's an example which I'm going to use. It was created by Luis way back in 1997. He didn't do it for this purpose, but I think it's a very good one. You can consider this as 3 boxes, which are the criteria, and you have your objects, the alternatives in them. Each of them have different amounts of the same component going into it, but here's the total intensity in all 3 boxes, and you're amalgamating them. So I have these 3. These are your criteria. These are your alternatives. Here are the true weights. And if we're going to do this in a hierarchy, it'd be something like this. I would fill in the objects and I'd create local weights. These are the local weights of the green area. These here are the local weights of the yellow area, and so on. Now that I got my criteria weights, I would say, okay, I'm going to multiply them by a weight for the I got my local weights. I'm going to multiply them by the weights of the criteria. What weights are going to multiply together to get these values here? Well, each cluster sums to unity. A 1 here does not equal to a 1 there. So my problem is, how do we get the valid cluster weights here? Well, here I'm doing it for the ideal mode. And I have picked out the ideal because I like the idea that it really identifies the unit. For example, when I express the local weights of box 1 with object 4 as a unit, it's the one with the most intensity in that area. These are the weights. Here's the weights here. Since the ideal units are in the colored vectors, I want to find the criteria weights for those units. If I can get the criteria weights for these units, then they will be established correctly. And then through that, it'll transfer up to the other ones to give you global weights. And so in this case, I am getting the weights here. The sum of the weights for all of them, for these links, and the red lines give the links, by the way, is 26. So 4 of the 26 creates this one. 8 of the units in this one has 8, and so it goes 308 and so on. I get my criteria weights up here. I do my multiplication, get my global weights. I sum them. I get my global weights, and when I renormalize them, I get exactly the weights which we said are the true weights. And so this bottom-up procedure, this is what was used by Belton and Gear in the original rank reversal article. This was this idea to locate the ideals and find the weights for the ideals. And note that these ideals become the links which will go across the various clusters of this hierarchy. Now, there's a thing called a linking pin solution. It was developed by Schoner, myself, and Chu. And what we did basically was we generalized Belton and Gear's idea so that any object of the colored vectors could be the link. Here, I've chosen object 2 for the first box, object 3 for the second box, and object 1 for the third box. So what I want to do now is I want to get criteria weights that measure these units, because that's what these are measured in, these units. And I do it up here. Object 2 has a intensity of 2 out of 20. Object 3 here has 8 out of 20. Object 1 has 10 out of 20. These are the weights. And when I use those weights with these links, I again get exactly the right renormalized results. So you can note that this bottom-up approach establishes criteria or weights that are dependent upon the links that you choose. So there's a relationship when you start this bottom-up approach between your units down here and what your criteria weights are going to be up here when you look at it from the bottom down. Now, rank reversal has been a big problem. It's, as you know, a change of rank of the composite results when you add and delete alternatives. We know it doesn't occur with a single criterion, and it doesn't occur with a linking pin mode so long as the links remain the same, okay? If the links remain the same, then the calculated global weights of the original alternatives will remain unchanged. Now, the top-down approach is a distributive mode. That's the usual mode we're associated with in AHP. Now for a long time, I kind of questioned this, but I think it is a valid technique, going top-down. But the establishment of the criteria weights at the higher level, that establishes a homogeneous scale that spans across the hierarchy. In other words, before I was concerned about getting a homogeneous scales that made commensurate units. Now I'm not. I'm just saying, how do I get a homogeneous scale across the various clusters of the hierarchy? Now, what then happens after you do that, the components of that homogeneous scale are distributed to whatever elements are down below. If alternatives are added or deleted, then the distribution below will be different again. Here's my example with the distributive mode. Now remember what I said before. now I'm not doing just any criteria weights up here. I am getting criteria weights for the units of these. Well, the units here is 1. The unit here is 1, and the unit here, but the 1 here, here, and here, they're different. So I want to get the units of this abstract object, which is the sum of all these objects. Well, the sum of all of these was 10, and sum of all these was 20, the sum of all these was 40, so those are the weights I'm using. And when I use those weights, I will get the correct answer. So that kind of reinforces the idea that the criteria weights should be measuring the units that are down below there for you. Now, here's the distributive mode, the same thing, and I have taken one object out, object 4. It's being removed. And I've renormalized my local weights to be 1 again. Okay, they're gone. When I do that, you notice what happens to my result. My weights here sum to 1, but they're not in the same ratio as before. Why? Well, look before. Before, the true weights, object 1 and object 3 were identical. They were equal. Here, they're not. The ratios have changed. So notice that local weights still sum to unity, but they take on different values. Okay, in here, they still sum to. These are the things that have changed. Different values for the same object means the units have changed. The units have changed in here. And the renormalization, in other words, a multiplication by a positive constant over there, produce a new unit of measure that is a new amalgamation of 3, not 4 objects. So we didn't change our criteria weights up here to represent there was only 3 here. This change didn't cause rank reversal, but the change did cause object 1 and 3 not to be equal. They should be equal. Now, the composite ratios over here, they change because renormalizations produce different units that in turn produce different composite ratios. If the change in ratios is sufficient enough, rank will occur. It did not occur in this case. So, do we have a problem? I think maybe we do. Because if you go back to the true weights, here they are with 4 objects. I took 1 object out. Here's the true weight with 4 objects. Notice that object 1 and 3 are still equal here. But what I got with the distributive mode, when I didn't change my criteria weights, when I changed my local weights, I get the wrong ratios. The ratios are wrong. They're not capturing it. So object 4 removed, it's changed. But the solution with priorities has object 3 larger than object 1, as you can see here. There's been no rank reversal. Note that, no rank reversal. But the composite ratios change. Why? The problem is not how the ratios change, not that ranks have changed. That's the problem is how the ratios have changed. It's not that the ranks have changed. And here's something I would like to claim. I think the rank reversal argument, in the rank reversal argument, we, the AHP community, have failed. I am part of that. I failed. We failed to analyze this kind of problem on a ratio basis. We failed to do the previous theme I talked about. We failed to use the full strength of intensities to analyze our problem. We resorted to a lower order of measurement. Basically, We adopted the other side's criterion. We analyzed it on the basis of rank. Had we analyzed the problem on a ratio basis, not ranks, I think we would have come to a clearer understanding of what's happening. The change in ratios is associated with the change in units, and that's why units become very important for us to consider. I'm making a case that units are important. Here's another one, and this is an entree to my next area. This is object for remove, but now I didn't change the original ratios. They don't add up to 1 anymore. This is in the unit of the 4 objects, and all of them are in the unit of the 4 objects. When I don't change the units, when I add or remove a object, I get the right answer. And what would happen if I added another object in here? Well, if I added an object to this pre-existing scales where the units remain unchanged, that's the point. Those new objects take their values in the same pre-existing units, not in different units because they haven't changed. And with units unchanged, there's no rank reversal. That is the idea behind what I want to talk to you next. This idea implies there can be a template hierarchy with fixed priorities, and that's my next idea. It's scales used as benchmarks, and there was a reason why this came up. Way back in 1996, Matty Bercasallo of Nokia complained to me that he tried to use AHP with his executives and they rejected it because there's too many comparisons. And he said, and Matty agreed with him. He says, we do this every time and our corporate criteria are the same for every decision, and yet we have to do the damn comparisons again. And so he requested some method to overcome this. And I worked on this idea, and it's from this that benchmark measurement eventually grew. It's based upon the idea of fixed units of measure. Now, there was a paper written by Tom entitled Scales from Measurement, Not Measurement from Scales. I thought it was a profound paper, but it was only published as a conference paper. Now, Claudio Garudi has picked up on that. He understood the significance of it. And he's written a paper that on his giving his reflections on this thing. I'd like to refer to this to tell you what benchmark is doing. Tom was referring to AHP scales being derived from ratio measurements of paired comparisons, not from measurements from some predetermined scale. That's the magic of AHP. You derive scales when you don't know the scale beforehand. So the ability to build these evidentiary scales with no prior scales is that intuitive magic of AHP. But my question comes from this, could you reverse the process? Once you have a scale for measurement, can you then freeze it and then use it as a scale for measuring? And that's what benchmark measurement does. So I'm freezing scales, okay? Getting fixed units, and then I'm going to use it. Now let's look at our fruit scale to see how I would do this. Here are all the fruits that were in that list. Here are their local priorities within their sizes. Here are different scales. They're just different scales that measure the same thing, just in different units. That's all they are. If I had an orange, would I have to put it in and do all the damn comparisons again? I say no. With that orange, it's somewhere between a lime and a grapefruit. It's going to go in here somewhere. I don't know quite where, but how would I fit it in to one of these scales over here? Well, one way would be to interpolate the distance between here and here. And so what percentage between lime, of the distance between lime and fruit, does this come in? And you could use that interpolation to put it in there. Or I could use paired comparisons. Now, the grapefruit is bigger than the orange, so I could say, how many times is the grapefruit bigger than the orange? Once I do that, I know the relationship of this to this, and I know what a grapefruit's worth. I can calculate what the orange is worth. Or if I need redundancy, I could say, well, how many times is the orange bigger than the lime? Same thing. I don't have to go through all the pair comparisons again to fit them into these priorities as benchmarks. I'm using these scales, and now I'm using that scale to measure this that's not part of it yet. If I wanted to, I could measure the orange to the small green tomato too. If you want redundancy to check it out, you can say, how many times is this bigger than the orange? You can do all those, but I don't think you need all of them. You need maybe one or two comparisons, and you can plug it in. So this slide just shows you can use interpolation, or you can use pair comparisons to determine where this would fit in between the lime and the grapefruit. And then think of it this way. If you had many fruits, a raisin, a plum, the orange, a banana, a pumpkin, you could fit them all in too by the same mechanism. Now, this is a little bit like a ratings model, except in a ratings model, we don't have actual alternatives down here. We have indicators of the alternatives, and we rate them for what they have. Here, we have actual alternatives, and we can compare any new object going into it to a real object, and we may get greater precision from doing that. In this manner, scales from PRM or measurements can be frozen as benchmarks and then used for measuring many additional items. Now, my theme 8 is on benefits and costs, and this is a very simple one. And I want to ask you a question. If I gave you the following benefit cost priorities for these 3 different projects and asked you which one would you select? Most people would look at there's the aggregate benefit priorities, aggregate cost priorities. Here are the ratios. Aha, project B looks like it's the best. That's what happens very frequently. But if I also told you these priorities you just looked at to get these, they came from these aggregate benefits measured in millions of dollars and aggregate costs measured in billions of dollars. Notice, in every case, the costs exceed the benefits, and the benefit dollar ratio to the cost dollar ratio is negative. Which project would you select? I think most people in business would say none of them. None of them are economical. But here, we would come to the wrong conclusion. This is the idea that this one and this one are not equal. One here is not equal to one there. Diederik van Malian, a researcher with the military research establishment in the Netherlands, has done a lot of work on this issue. But you got to be careful how you use these if you don't know that the units are somehow commensurable. My last theme, and I'm not going to spend much time on this, I may have time for some questions, I'm not sure, but is on the similarity of hierarchies and networks. If you look at AHP, I'm not going to go through all this, but think of it this way. Both AHP and ANP get their local weights from pairized ratio matrix. In a hierarchy, you put them on a level, and you call them local weights. In an ANP, you put them in a supermatrix, and you call them an unweighted supermatrix. They haven't been weighted yet. If you look at the global weights of a AHP, they're the analog in a supermatrix is those are your weighted column values. The weighted column values are basically global weights. So the process is the same. Where the difference comes in the aggregation in matrix multiplication used for the ANP, whereas you use a weighted sum model for the hierarchy. But Orrin Cooper and myself have been throwing around these ideas of looking at the supermatrix as a series of hierarchies. Here is a supermatrix for a problem we worked on using those fruits and packages of the fruits. There are 3 packages, and this is the unweighted supermatrix because the columns add to a number down here. We would now weight these columns and get them to change. But you can think of this column, it's got a unit of 1, or not at the moment, but it will once we weight it. And that can be looked at as a hierarchy by itself. This is another hierarchy. You can look at each of these as a hierarchy, these columns. And the question is, what weights will get you a solution for this? Well, when you get the stable solution and put this in as weights for this one here, you will get the results that repeat that. But that's very much like Tom's proof of the pairwise ratio matrix, is that the eigenvector will reproduce itself in hierarchical composition. Well, the same thing applies to a supermatrix. It will do that same thing. Some conclusions I have. I'm down to the end now. I'm surprised I'm here without being told I'm over time yet, but
no, you're good. You have 5 minutes left, and there's already one question in the chat.
Okay, I'll be willing to entertain it. AHP, this is Orrin Cooper's statement. I thought it was interesting. It's a very broad statement. He says can be simplified to one sentence. A method that links, connects, aggregates objects together using priorities from relative comparisons. Ultimately, that's what we're doing. Ratio scales derived from PRMs are like magic, and the scales make evidence where none existed beforehand. I read Yoshi Ida's paper, and this term came up and it struck me quite strongly, saying we're making evidence where none existed before, and that's a useful property. Another conclusion I want to emphasize that any change in priorities via multiplication by some positive constant transforms the measures to a new scale that has a different unit of measure. And to get a better understanding of what's happening, follow that unit and understand it, because that can get us places. And to get the full power of AHP and ANP, use it in its ratio form, not in a lower order form, and get the intensity of one object over another. That's what we want. Now, maybe my ultimate conclusion is kind of a call to action. I've been around for a while, and I've realized it's there, but a lot of people ignore it. The unit is there in our ratios. It's not going to go away. We need to recognize it, and we need to address it. Remember, I like that Sajjad Zahir statement. A 1 here is not equal to a 1 there. The ones are different. The dilemma is that the unit's obscure. I've attempted to show where mistakes can be made with an obscure unit, and I could try to show where beneficial procedures can occur if the unit is recognized. I want to call the AHP community to action. To continue to ignore the issue of units, I think, is dysfunctional. My hope for this session is that I have created some functional inconsistency, and I want to emphasize the functional part in your mind about the advantages and disadvantages of the unit. I know that this type of functional inconsistencies has been central to my career, and I think that maybe it's capable of catapulting AHP and ANP to new frontiers. I am very positive and strong about the power of ratios. That's our power. Let's use it. I think there is a bright future for AHP and ANP. And thank you, and I would be pleased to handle questions.
Dr. Karpak, would you like to?
Yeah. I already wrote it, and maybe everybody can see. And,
I can see.
Yeah. Hi, Professor WEDLEY. Although
Hi, person.
Belton's paper published, and I heard from her that what she wrote there is not correct. She just said, I wrote Belton, Valerie Belton, in one conference, She said that she wrote it in when she was a young PhD, but what she wrote there is not correct. But she mentioned that it has been referenced quite a lot of people. So I'm asking if there is anybody in the audience knows something about it better yet, what they think about Belton's paper, what she published. I think it was a long time ago. Maybe you have a comment, Roseanne, about it. Yeah.
Yeah, I was actually there. Maybe you and I were in the same session. I'd been giving a talk about relative measurement, and I was arguing against a rank reversal, saying that was some kind of non-issue. And Valerie Belton was in the session, and she stood up at the end of my talk and said, you know, I really misunderstood. I didn't understand when I wrote that paper. I'm so sorry, because people have just taken it and they refer to it as if it's correct. And she said it wasn't. I don't remember now what her paper was, but she verbally said that to me.
I remember, this is Luis, I remember the situation because Tom and I replied to the paper when it was first published. But the solution that Pat Harker and I found was using an ANP model, if you recall. But the only situation in which you would know the rank reversal was acceptable was that you knew the actual values of the measurement, you didn't have them in relative terms. Now what they did is that they made it into relative terms. So you make a copy, you add the copy to the situation, that happens, right? But that's because the criteria weights were changing. So what they wrote there was enlightening in the sense that they give you an idea that perhaps there's a rank reversal, which is what Tom was saying all the time. You have to accept that. The theory says you accept intransitivities, right? But if you want to preserve rank reversal, a necessary and sufficient condition for rank reversal not to occur is if the matrix of pair covariance comparisons for a single matrix is row dominant. If you preserve that row dominance as you add alternatives, then you have no problem. The only problem is that if you have multiple criteria, you can have rank reversal because things change. So if the criteria weights as you compare the alternatives, like happens all the time, then you have to have a feedback loop. And that is basically an ANP with a loop, basically. And that's how the only way I see the solution. I agree that, Bill, you got it with the linking pins and so on, but since everything in the AHP is about raising the matrix to powers, right? You take the pairwise comparison matrix, you raise it to powers, you get to the eigenvector. And right. The principle applies to the ANP. So I agree that the structure of the matrix in the supermatrix could be difficult sometimes, but nonetheless, that was the idea. So I don't think a paper was completely wrong in that sense. They wrote something they perceived, and then Valerie Belton, I agree. I was in the session when that happened, when she backtracked and said maybe we shouldn't have written it without talking to Tom. But you know, when you are younger and you want to get a name, what do? You try to take the guy who has the name, and that's the reason why it happened.
Yeah, I'd like to mention a couple of things. For a long time, I did not appreciate the distributive mode. I believe it's correct, but it does cause rank reversal. It can happen, but that's a legitimate way of doing things. But you got to recognize that if you're distributing downwards and you're just to whatever is there, you're going to get different units down there. And when you get different units down there, the portions are going to be divided up differently. And the ranks are going to change. It'll happen.
Yeah, there was a colleague from England who said, what happens if you reverse the problem? You have three alternatives and you cut it down to two and you make a different decision. But this is like when the judge says, you heard the answer from the witness, but do not consider the witness comments. They're discounted from the record. Well, once you have the information, you have three alternatives and you make it down to two, you can't tell me that you cannot consider three because I'm aware of three. So that's, you know, the rank reversal issue, as I said, is either a mathematical problem or you can explain it within the context. Yeah. I'm in favor of accepting rank reversal. I think that information is always going to happen. So
rank reversals happen. People's preferences change. It happens all the time.
Right. Kahneman and Tversky said it very clearly. If you think in the positive term, you get one rank, and if you think in the negative term, you get a different rank.
But what I would urge is what happens to those ratios that we have? Did we intend them to be changing? It has to be a problem for which, we would allow that to happen. Rank reversal is only a symptom of the problem. It's not, it's a change in ratios that happen.
It is true, but in the situation where you have no scales, you are building them up by using pair comparisons, right? It is the scale of the user, the guy, of the decision maker. But if you bring different people and they don't agree on their judgments,
That's
then
right.
you have a different scale, right?
Mm-hmm.
So that's the reason why, yes, it is true that you can have a scale for everybody and agree on that scale, but at the same time, not everybody might agree on what that scale is about. That's the reason why people like to have measurements for weights and length and distances, because they all agree on one thing, right? That's Lebesgue put it very clearly. You map your experience when you're observing to an infinite number of possibilities.
Excuse me, guys. This is very interesting. I wish we had hours to discuss it, but in 5 minutes, our next session is going to start. Bill, that was a terrific talk. Thank you so much. But can we wrap it up now?
Thank you very much for allowing me to be here. It's been a pleasure. I hope I have given some people some ideas and different possibilities.
Always, Bill. Thank you.
Thank you.